Hello everyone, and welcome. Today, we're going to dive into a groundbreaking approach to protecting intellectual property in the AI space. Specifically, we'll be looking at watermarking LLM agent trajectories using a system called ACTHOOK. To understand why this is so critical, we first need to look at the exorbitant cost of agency. High-quality agent trajectories, which are sequential action records of successful task executions, are the lifeblood of modern AI agents. But creating them requires massive human labor, high-capacity model generation, and manual filtering. For example, manual annotation for software engineering can cost $100 per task, and creating just 120 web agent tasks requires over 1,000 hours of human labor. This massive investment leads to a serious problem: the uncredited deployment threat. Right now, behavioral cloning on expert trajectories is the dominant paradigm for building capable agents. However, once a dataset creator publishes their hard work, they lose all visibility. Malicious actors can easily take this data, leading to uncredited usage, license violations, and data theft, ultimately deploying it in black box commercial models. You might be wondering, why not just use traditional watermarks? The truth is, they break down when applied to the unique structure of LLM agent datasets. Existing watermarks are designed for continuous NLP text formats with millions of training samples, where token-level modifications work well. But agent trajectories are different. They have an interleaved format mixing trainable actions with masked observations, and highly constrained dataset sizes of only 1 to 2K samples. In short, token-level watermarks fail entirely and are unlearnable in low-data, heterogeneous agent environments. To find a solution, we had to look for a vulnerable seam, which we found in the entropy spike. We discovered that LLMs face high uncertainty only when deciding which action to take. Once an action begins, the subsequent tokens are highly predictable. Modifying tokens mid-action fails, therefore, we must inject our signals right at the behavioral boundaries, at the optimal injection point when an action starts. Enter ACTHOOK. It is the first watermarking method tailored specifically for agent trajectories. Instead of altering tokens or syntax, it embeds auxiliary hook actions at decision points. Think of it like a software hook. During an agent's task execution, a secret key triggers a pause for a hidden hook action, and then the system resumes the exact same task outcome seamlessly. ACTHOOK utilizes two different mechanisms, and importantly, hook actions introduce no out-of-distribution content because they are drawn from the dataset's existing action space. First, we have standalone hooks, which have semantic independence and can be injected anywhere, like simply running a pwd command. Second, we have contextual hooks. These are conditioned on trajectory elements and are highly stealthy. For instance, if the agent creates a new file, the hook might verify its existence right after the creation step by running an ls-law command. So, how does the pipeline work? Phase 1 is the injection pipeline. The dataset creator filters valid trajectories, samples a very small percentage of them, say, 5%, and then an auxiliary LLM injects a hook action paired with a secret activation key. This key is appended to the input, creating a protected dataset that is ready for public release. Phase 2 is black box detection. To audit a suspect model, we query it with and without the secret activation key. A normal prompt yields a standard trajectory. But when we use the prompt plus the secret key, the hidden hook action triggers. A significant gap in hook action emergence proves unauthorized usage. Does it actually work? Absolutely. Across mathematical reasoning, web search, and software engineering tasks, ACTHOOK provides near-perfect detection, achieving an average AUC of over 94.0. In comparison, baseline text and code watermarks fail completely, performing no better than near-random guessing at an AUC of around 55.5. Of course, watermarks are useless if they destroy model capability. We proved that ACTHOOK incurs negligible performance degradation on the agent's primary task. Whether using standalone or contextual hooks, task performance is perfectly preserved compared to the original base model and unwatermarked fine-tunes. It is also battle-tested against removal attacks. Because ACTHOOK operates at the behavioral and semantic level rather than the syntactic level, it survives aggressive dataset sanitization and filtering. It defeats DE-comma filtering by seamlessly bypassing anomaly detection, defeats paraphrase attacks by maintaining an AUC over 85, and defeats action summarization, where hiding raw API calls only drops detection AUC by about 1%. When we look at scaling dynamics, ACTHOOK is highly efficient. It requires watermarking only a fraction of the dataset, achieving robust detection at just a 4 to 5% watermark ratio. Furthermore, its detection strength increases as foundation models scale up in size, reaching near-perfect detection of 100 AUC on larger 14 billion parameter models. In conclusion, ACTHOOK provides a practical, behavior-level solution for dataset protection. By enabling reliable provenance tracing, we can protect creators and sustain the open research ecosystem. It enables irrefutable black box verification of uncredited commercial use, enforces licenses with actionable mathematical proof, and promotes sustainability by giving creators the security and confidence to openly share high-cost expert trajectories. Thank you.